Hello, in the last videos we discussed some questions on DP on trees. Let's discuss the next one. Here are two questions from Codeforces. I will attach the links in the description below. Misha has found a binary tree with n vertices numbered from 1 to n. A tree is simple graph with n minus 1 edges and n vertices. Each vertex has degree at most 3, whereas the root is the vertex with number 1 and it has degree at most 2. Unfortunately, the root got infected. The process can happen in times. Misha either chooses a non-infected vertex and deletes it with all the edges which have an end in this vertex. And then infection spreads to each vertex that is connected by an edge that is already infected. Return the number of maximum vertices that he can save from the infection. Note that the deleted vertices are not counted as saved, and the constraints are n is up to 3 into 10 power 5. So, given a tree, initially the root is infected. And then in each operation, the infection will spread from a node which got infection and which is directly connected to it. So in this, let's take this one. In this, the initially t is 0 and the root is infected. So if t is equal to naught will happen, the infection will spread to the next one which is directly connected to this. So now this is also infected. And now we can do an operation. So in 1 second we can just remove it, right? So if we remove, then these three will become independent, and hence these will not be connected to this node anymore, and hence these three can be saved. So the answer for this is 3. So in 1 second it will spread to any other direct node, and then in the same second we can do an operation. So in that way, by doing operations correctly, we have to return the maximum vertices that we are able to save. So here these two we are unable to save because this is already infected and this is also infected in first second. So the answer is only 3. These 3. So, and also it is given that each node can have only degree at most 3. 3 in the sense 1 parent and 2 at most children. And for the root there is no parent, so the degree for root is at most 2, and for other the degree is at most 3. For this the degree is 3 because a parent and 2 children. So how can we solve this? As the degrees are very small, let's think what will happen for each degree and then we can think. So this is the first type where root has no child, and here is the second one where the root is having a single children, and here is the case where we have 2 children. So in this case, what is the answer? It is simply 0 because the root is already infected, and there is even in after 1 second there is no node to get affected, or we cannot save any nodes because there is only one node. As it does not have any child, we cannot save any children, any node in this tree. So the answer is 0. And coming to second case, the root has one node, one child. So now what can we do? So as we discussed in the example, in first second it will get infected, and in the first second after getting infection we will remove this. So the answer for this is 3. So the maximum count, the number of nodes we are able to save is 3 here. But here we have two choices, right? We can save this after infecting, or we can save this after infecting. So how can we select which one to remove? It is very simple. So instead of thinking about which is better, we only have two choices, right? So what if we try the both? We will try both and then we will think what will happen, and we will select the maximum. Because if there are many different, for example, if the degree is at most 100 or 200, then we can think that we can do based on some sorting or something. But here it is at most 2, so we are very sure that we can try choices. There is no harm in trying choices, right? So how can we do this? So when we are at root, we will go through all the nodes we have and we'll store a simple vector to know whether it is of size 1 or size 2 or size 0. We can check it manually also, but this is very simple because we can just push all the nodes into the vertex, and then after completion of DFS, why we are doing DFS, let's discuss that also. For example, we are at this node, right? We are at this node, and then after 1 second it got infected. So how can we find the answer in this? It is simply the size of the child node, right? It is simply size of child node minus 1, because we are unable to save this, and if we remove this, then all other nodes in the subtree will get saved. So in this way, what is the count of nodes that are saved? It is simply the size of child minus 1. Size of subtree rooted at child minus 1, and which is also simply equal to size of subtree rooted at root, which is 1 minus 2. Because initially root is infected, we are subtracting 1, and again this is also infected at first second, so we will remove this also. So the rest of the nodes we are able to save is the total size minus 2. So in this way, if the root has no children, the vector size will be 0. So we can simply return 0 because we are unable to save any node. And if the size is 1, then this is the simple one, size of root minus 2. So how we will find the size of the root? So we can use DFS. So for example, we have this and we have 3, let's assume that we have 3 different children. So if we find the size of this, if we find size of this, and if we find size of this, it is very easy to find size of whole this, right? It is simply size of the child 1 plus size of child 2 subroot subtree plus size of subtree rooted child 3 plus 1 because of this now. So in this way, if we try to do simple DFS, then we can store the sizes of every node there, and then by DFS at a single node we can try to store the answer from the size of children, and then we can find the size of root. So in this way, if the child is size is 1, we can simply return size of the whole root, whole the tree minus 2. But what if the size is 2? What if the root has 2 different children? And then let's say in the first second we decided to remove this one. We decided to remove this edge. So this is infected. So what is the nodes that we are able to save? Let's assume we have two children, right? So this is child 0 because we are storing in a vector. So this is 0 and 1. Child 0 and child 1. So we have two choices. Save child 0, like save the subtree rooted at child 0, or save the subtree rooted at child 1. Let's discuss both the cases and let's check which is better. So if we remove this one, if we remove this edge, then what is the number of nodes that we are able to save? It is size of child 0 minus 1. This is simply, we are unable to save this, we are able to save all the rest of the nodes in this subtree. So with respect to this subtree, what are the nodes that we are able to save? It is size of child 0 minus 1 can be saved. And then, but in the same second it will spread to this also. Right, in the first second, it will spread to each and every node that is directly connected. So even we are unable to save this, but we are able to save this one. And with respect to this child, what is the number of nodes that we can save? So we can use recursion rate because this is exactly the same case with this one. This is exactly the same case. Given the root is infected, we want the nodes that can be saved in this subtree. This is exactly the same one we thought of. So simply we can use recursion. So what is the number of nodes that we can save from this? It is simply function of child 1. So we will call recursion in this, and then it will think again, like it will check what are the roots, what are the number of children, and then it will call the recursion, and then it will call leaf and so on. So in this way, at a given road, we can think of two choices which to select, and these are the total number of nodes that can be saved because function of child returns the number of nodes that we are able to save. And what if we try to remove this edge? If we try to remove this edge, then what will be the number of nodes with respect to this subtree that we can save? It is simply size of child 1 minus 1, child 1 minus 1. And then with respect to this subtree, what is the answer? It is simply the function of child 0 minus 1. Sorry, the function of only child 0. Because simply this is simply the recursion where it returns the number of nodes that is able to save in this subtree. So we'll add this both. So in this way we got two choices. Which one to select? So simply select the which one is maximum. So maximum of size of child 0 minus 1 plus function of child 1 and size of child 1 minus 1 plus function of child 0. So in this way we can simply use our DFS to find the answers, to find the sizes of children subtrees, and then we can add all in the present node subtree size, and then based on the number of children we have at the root, we can decide which one we are going to remove. If it is 1, we will simply use this one, size of root minus 2. If we have 2 children, then we will take maximum of this both. So let's check the code. We are simply inputting n and then inputting the edges and adding an adjacency list, and then calling the DFS 0 and minus 1. Minus 1 is simply the parent, so that it will not reach any other node because there is no node with minus 1, right? So from 0 it will reach all the nodes which is attached to minus 1 because there is no parent for 0, and then simply return the DP of 0. It means that what is the number of nodes that you are able to save when the subtree is rooted at 0, and we are simply clearing the adjacency list for next test cases and then resizing. So let's check DFS. So this is also very simple. When we are landing into the subtree for first time, a node for the first time, size is 1, so the size of node is 1, and then make a child vector and then travel through all the adjacency list nodes which are directly connected, and if it is not parent, then do the DFS. So when at the time when we are coming to this, what will be stored? The size of IT will be stored. So the size of every child node will already be stored, and then we are pushing this into child, and then add the size of node to add the size of subtree to the present root subtree size, and then initialize the size is 1, so it is simply 1 plus size of all the children, and then find the number of nodes, number of children the present node have. If it is 0, then simply return, because we are unable to save anything. Return simply is returning 0, right? And then if the size is 1, so if the size is 1, then dp of node is equal to size of node minus 2, because node is already infected. In 1 second, the single child which is directly attached to root will also get infected. We can't save those. We can save all the nodes except those two. So size of node minus 2, and then two children. So we have two choices: size of child 1 minus 1 plus dp of child 1, size of child 1 minus 1 plus dp of child 0. So in this way we can simply return the answer. So let's discuss the next one. We are given a rooted tree consisting of n vertices numbered from 1 to n. The root of the tree is the vertex 1 and the parent of the vertex v is pv. There is a number written on each vertex. Initially all the numbers are equal to 0. Let's denote the number written on the vertex v as av. For each a, we want av to be in the range of lv and rv. In a single operation, we can do the following. Choose some vertex v, and b1, let b1, b2 and so on bk be vertices on the path from the first vertex, which is root, to the present vertex we are selected right now. And then choose a non-decreasing array C of length k, 0 greater than equal to less than or equal to c1, less than or equal to c2 and so on. And for each I in the path, increase abi by ca. What is the minimum number of operations needed to achieve our goal? So it is giving that initially there is a tree with rooted at one node, and then it is given a parent vector. So for I, parent of I is the parent of node I, and then initially all the numbers on vertices are 0, but we have to do some operations, and finally there finally the condition should be satisfied where every node value should be between from LV and RV. And in a single node, in a single operation, what we can do, let's say we have this tree, right? So we have very big tree. So what the question is saying is, let's select this one. Let's assume that we are selecting this one in the present operation. So if we select this node, what is the path from root? It is simply this one, and this one. In this way we can reach the node that we selected. So this is the path that we are selected. So now what we have to do? So we have to select a non-decreasing array C such that, let's say this is C1, we are adding to this node C3, C2, C3 and C4. There are 4 nodes in the path, so we are selecting 4 values, and these 4 should be in the non-increasing order. So it can be 2 to 3 or 2 to 3, 5 and so on, but it cannot be 2, 1, 1, because it should be non-decreasing. It means that the next value can be same or the next value can be increasing. So this is some kind of non-increasing one. So we can select this, and then for this root, for this node, we have to add C1 to its value. For this node, we have to add C2 to this value. C3 should be added to this node. C4 should be added to this node. So in this way, we can do any number of operations. And then after doing all the operations, one condition must be satisfied. What is that? For every node, the final value on that should lie between L and R of that respective node. So for every node, we have two values. The first one is L, the first one is R. So for the root node, we have L1 R1. For first node, there are L2 R2 and so on. And what does those mean? That means that after doing all the operations, the values of those respective nodes must be within that range. Only then we can return the answer. Else we have to do still more operations. So in this way, we have to return the minimum number of operations where we can get the condition satisfied. So select some node k and select some non-decreasing values and increment all the nodes by selected values, and then return the minimum number of operations to make all the values with values L inclusive between L and R. It can be L, it can be R, it can be between. It cannot be any other values. So hope you understand the question. Else read again. Let's discuss how can you read it. Let's discuss how to read it. So let's say this is the tree, right? So if we select this node, then what are the nodes that will be affected? All the nodes from root to this node will be affected. So all these four will be affected. But if we select this, then what will be affected? Only these three, right? And if we select this, then only these two. If we select this, only this then. So from this, which is difficult to change? So this node can be changed in four different ways. This node value can be changed in three ways. This node can be values can be changed in two ways, and this node value can only be changed once. And when once is the time when we selected this node. So if we select this node, only then this node will be affected, but not with this one. If we select this node, this value will be can automatically be affected. So it is comparatively difficult to change the value of child node, because for changing the value of child node, we must select operation to do from root to child node. But all the nodes in the middle can be subsequently done the operation in this itself, because in the same operation we can select all the same value, and then maybe the condition is directly satisfied for all the nodes. But the main thing is the child is difficult to change here, because only in one path the value will be affected. I am saying not one operation, but in the one path. This path can be selected many times, but it can be selected only when we select the child node, leaf node, but not any other node. So prioritize leaves first, right? Because it is difficult. So why not think from that? So let's say we are thinking about this one. So we discussed to do operation from root to leaf node. But we have many different operations that we can have. We can add 5, or we can add 4, or we can add 6. So which one we will add, and why we'll do that one? And also, what about the values that we will add to this? Because this is complex, right? We can select any values, 1, 2, 3, 4, this is possible. 0, 0, 0, 4, this is possible. 4, 4, 4, 4, this is possible. There are infinite different options, but which we will select to reduce the operations. So here anything is fine, right? Because we can select 4, or we can select anything here, and 2 and 4. We can select anything, and 3 and 4, 5 and 6 and so on. So everything is fine here. But we want minimum operations. So let's say we have this big root, big tree, some big tree. So the values of this node are L is equal to 14, R is equal to 20. For this L is equal to 2, R is equal to 6, LR. So there are three different child leaf nodes. So let's discuss what is the let's discuss some configuration. So let's assume that we're adding 2 here, and we're adding 4 here, and we're adding 3 here. So here 2, here 4, and here 3. Let's assume we are selecting the least one for now. So if we are adding 2, 4, 3, what is the maximum value that this node can be achieving? It is also simply 2 plus 4 plus 3, right? Why? Because we have to select non-increasing values. Here we have selected 2, so the maximum value that here we can select is also 2, and here we selected 4, so here also the maximum is 4, so we are selecting 4, and here also 3. So what will be the final value of this node? It will be 2 plus 4 plus 3, which is 9. So if we select the least values, the value that we are able to achieve for the parent node is 9. But the L and R values of this is 14 and 20. So we are unable to make this true. We have to do other operation again. But what if we try to select the maximum values? So if we try to select the maximum values, then what? So 6 here, 5 here, and then 6 here. And then what is the maximum value that we can get here? It will be simply 6 plus 5 plus 6, which is 17. So if we select this, then no need to do other operation for this, right? Because directly 14 and 20, 17 is in the range of this. And in simple 3 operations, one for this, and one for this, we are able to achieve value for this also, which is very good. So from this what we got, even if we have many other choices, it is always better to choose the highest value for leaf nodes. Why? So that the above root can be decreased by doing an operation. Because here, if we are selecting the least values, then we are able to get 9 for the node, but the values are 14 and 20. So even now we have to do extra operation. But here, if we are able to use highest values for the leaf nodes, 6, 5, 7, 6, the value is 17 and there is no need to do operation. Even now there may be a case to do operation. Let's assume the values are 30 to 40 and then the leaf values are same. So even now the maximum value, the root can be made is 17. Even now we have to do operation. But this is surely better than the before case where we are getting the less value, which is 9. So from this, the final value of leaf is R of I, because it will help its parent to get less number of operations. So this is the first observation we got. And then, so if we are at root x, if we are at node x, it will be better if the children final value are already known. Because how we are able to select 6, 5, 7? Because if we are able to get these, only then we are able to get some 17. So when we are doing the operation at node 17, some node, we have to know the final values of before leaf nodes or child nodes. So if we know the values of these, and then we can think what is the maximum operation what is the maximum sum we can get at this node, and then we can think what are the operations that can be done at this node. So for a given node, when we are finding the answer, it is better to know the final values of the child nodes itself already. So we can start doing DFS so that we'll get the answer for child, and then we will start finding the answer for parent. So child 1, child 2 are the values of children. And what is the maximum sum that can be achieved? We already discussed that. It is simply child 1 plus child 2 and so on without any extra operation. So this is the maximum value that we can get without any extra operation, which is the sum of final values of all the children. And so now let's discuss some other cases. So let's say we have this node and the values are L and R, which are unknown. So we have to select L and R. Sorry, we have L and R, but for different cases, let's discuss different scenarios. So if the values are 2 and 6, if the values are 4 and 4, if it is 1, 2, 1, 2. So what if the range is 3 and 15? What if the range is 3 and 15? So by doing DFS, we already got that we are setting 6, we are setting 4, and we are setting 2 for the children. So what is the sum here? The sum is simply 6 plus 4 plus 2, which is 12. So the sum is 12. And now the first case is sum is lying in the range L and R. So the sum is lying in the range L and R. So what we should do here? There is no need to do anything. So there is no need to do any operation. But if the range is 3 to 10, so if the range is 3 to 10 and the sum is 2, the sum is 12. So we cannot do any no need to do any operation. No need to do operation, but this is violating our condition, right? So should we return -1? No, because the maximum value that we are able to achieve, the maximum value is 12. We can achieve 11 also, we can achieve 10 also, we can achieve 9 also, and simply we can achieve 3 also, which is the least value. So sum is just the maximum value. So, but if the range is L and R, we can decrease the values, because for now what we assume, when we are selecting 6, 4, 2 for the child, we assumed that we are selecting 6, 4 and 2. But no, if the range is 3 to 10, we'll select 1 plus 1 plus 2. What is the harm in this? The final value is 4, which is in the range. So even if the range is, even if the R is less than the sum we got, there is no problem. We can decrease the values. So simply no operations, right? We can simply use 1 plus 1 plus 2. This is not a contradiction, but we can decrease the values. And then what if the values are 15 and 20? So the sum is 12 and the L and R are 15 and 20. So then we have to do operation, because the least value we are able to get is 15. Like we should get is 15, but we landed at 12. So we have to do extra operation. So now we decided about extra operations. But when we are going to the parent of this node, we want the final value for this node, so that we can follow the same criteria we followed here. So at every node, we have to do main two things. The first one is what is the extra operations required to add this one for this node, and then the second one is what is the final value of this node after doing the operation. So if we know these two, and then it will be easy when we reach to the parent. And now what is the final value for the children or for the root in these three different cases? So for 3 and 5, so the values are 3 and 15, the sum is 12. So the sum is 12. So we already discussed that it is always better to give a node with a maximum value, so that for its parent node the operations can be minimized, which is exactly we discussed in the leaf nodes. Why we are assigning 6 here? We are assigning as maximum as possible, as maximum possible value, because the parent node can be reduced the number of operations. So here we have selected 4. So here we have selected 2. So our main goal is to maximize the value that we can assign to a node so that its parent will be beneficial. So for 3 and 15 and the sum 12, what is the maximum value? Is the maximum value 15? No, because R is 15, but the maximum sum we are able to get is 12. So this is the only maximum value that we are able to get. So this is the only maximum value. So 12 is the final value. But what is the L and R 310 and the value is 12. So if it is 12, then we can only select 10 because the node value should be between L and R, but we selected more value. So we can minimize this one. So simply the final value will be 10 because this is the R we can have for this node, which is the maximum value. So we'll ultimately boil down the final value for this node to be 10. So the final value is 10. And then if the range is 15 and 20, so if the range is 15 and 20, the sum is 12. So ultimately we have to do an operation because it is not in the range. So finally, which will be the value of the node? It will be simply 20. So we will select 8 for this node. Why 8? Because we discussed that it is always better to do the maximum value. So here we are anyways doing the operation to get the condition satisfied. So why not do the operation to get the maximum value itself, so that in one operation we can achieve both things. In one operation we are able to achieve the highest value, and in the same operation we are able to achieve, like we are able to reduce the operations for the parent node, which are both are same. So if the range is L2R and if it is less than, if this is more than sum, we will obviously do an operation, but we are making sure that the final node of this value is the 20, which is R, so that the parent node will be selected, will be effectively reduce the number of operations. So final value is 20 for this, and then we are increasing the operations. Here no operation space because no need to do operation. Here also no need to do operation. So in this way, by simply observing some things, we discussed how to get the final values of the nodes, how are we able to select a path, and then how to find the number of operations. So hope you got it. Let's check the code. If you have any doubts, comment below, and then simply input the values and edges, and then resize all the values and initialize the final values with 0, and then input li and ri where it is the least value and highest value for the node, and then function of 0 and -1. It is simply DFS of node 0, and then sum is 0 and answer is 0. Answer is simply the number of operations and sum is 0. What is sum? It is simply the sum of all final values of the children node. So we are looping through the children. If it is not the parent, add the number of operations. So answer press is equal to function of IT node. It indicates the operations for child subtree, and then increase the final value in the sum. So sum press is equal to final value of node. So in this way we are finding the sum as the total final values of all the child nodes. After completion of loop, if the sum is less than L of node, so if that is the case, then we have to do operation and increase the answer, and then what is the final value of the node? It is simply R of node. And else, if the sum is less than R, it means that it is already in the range L and R. So if it is in the range L and R, we can't do anything. The final value is simply sum, because that is the maximum value that you are able to get. And else, final value will be R of node, because this is greater than R. So simply we can reduce the sum to R of I. So it is simply R of node. And then simply return the answer. In this way we can return the answer. If you have any doubts, comment below. See you in the next video.